All right. How would you like some homework?
Yes.
I wouldn't, but I guess.
I'm not really.
Been chomping at the bit for some homework?
I mean, I don't know. It's been a while since we've had homework, so maybe it'll be fun. I'm trying to be.
Why is our class for that Tuesday?
I don't know.
Our theory class had like what, Dr. Joe, 5 people?
I think we got it 6 by the time we were done, but 9.
Oh, we're doing homework out of the book this time?
Yeah.
And the worksheets.
And other worksheets.
Ew.
What is wrong with you people?
Is today Wednesday?
Who likes to do homework?
So yesterday was the 29th.
Yes.
Hey, tomorrow's Halloween.
That's Wednesday, yes.
I didn't have anything.
I have like a lot of
We didn't have theory on
Fridays,
No.
Thursdays.
I'm gonna get you homework on Friday. I wanted to get through this stuff.
Is it going to be a lot? Because the last theory homework wasn't bad. It was only like, what?
Is our
probability
probability test the week before Thanksgiving?
It's 16.
14 around 16.
Yes. 6, 14, 16, 18.
6, 14, 16, 18.
Yes.
Our Thanksgiving break starts on Wednesday, right?
Yes.
Right.
I might tell Dr. Olson that I'm going to be sick on Tuesday.
Now that everyone else knows. It's funny.
When's 11/6?
Wednesday. It's a week from today.
Wait, the test is?
No, when the homework is due.
I was like, wait, that's really fast.
No, the test is the night. Yeah, it's the Tuesday before Thanksgiving.
It's our last test.
Is anybody in my CS?
Yes.
So then,
Did we have one?
It's the
our last
computer
that's our
yeah.
last test.
It's not the Tuesday right before Thanksgiving. It's the Tuesday before.
But he didn't have
It's the
that.
19th, not the 26th.
Oh.
Right?
So I'm gonna go with-
There was like some post.
I wasn't going to give you a test on the Tuesday for break.
Thank God.
Did he say anything about it? I left
You
early.
didn't say anything about it.
No one would be here
So I'm
anyway.
gonna do it.
Yeah.
Dr. Olson's having hers next week and then the week after Thanksgiving, so that's kind of nice.
All right. Let's see if we can look at this particular. This one's out of the book as well, but it goes back to the chi-squared stuff that we did in the previous section. So this is 3.6-17. It's in the normal distribution section, but it talks about the theorem that we talked about. I'm sorry, it involves the 2 theorems that we talked about right at the end of class last time. Plus, it gives me an opportunity to go back and look at that chi-squared table again so that we know how to read the table. All right, so it tells us that the random variable x has a normal distribution with mean 7 and variance 4. So remember that that's the notation. When we have that, just that capital N, that's telling us that we have a normal distribution. The first number that's listed is the mean. The second number that's listed is the variance. And it wants us to know, it wants us to find what the probability is that if I take x minus 7 and square it, that value is going to be in between 15.364 and 20.096. All right, so the 2 theorems that we talked about at the end of class last time was, one was converting any normal distribution to a standard normal distribution. And then the second one was, if we square a standard normal distribution, we get a chi-squared distribution. Right? Those were the 2 theorems that we talked about right at the end of class last time. Okay? All right, so what have we done here? Well, anytime that I have a normal and I square the distribution, we should immediately think that we're going to generate a chi-squared distribution out of this somewhere. Okay? So anytime that we do a square, it's just what should pop into your head when you first think it. Because we know the square of a standard normal is a chi-squared on 1 degree of freedom. Okay? Anytime that you see a square on a normal distribution, we should get a chi-squared distribution. So that's where our mind should go as far as a way to attack this problem. So since I'm seeing the x minus 7 and squaring it, that's what's making me think chi-squared. Okay? But to be able to get to a chi-squared distribution, the thing that I am squaring has to be a normal distribution. Right? Not only normal, it has to be a standard normal distribution, right? So remember, we get the standard normal distribution by doing what to the original random variable? What do we do? What do we do to get the standard normal? What do we do?
Z score.
They do the z-score idea, right? So what do we do to get that?
X minus mu.
Good. You subtract the mean, and then you divide by the standard deviation, right? Okay. Okay. Inside the squaring, what's been done? They subtracted the mean. Have we divided by the standard deviation inside the square? No.
Well, yeah, because what if it's 1?
Is it 1?
But it's not.
Oh.
Is it 1? No. Okay. We haven't divided by the standard deviation. So to make the and notice I'm concentrating on the inside right now, right? So to make the inside standard normal, what do I need to divide by here?
2.
In the inside, I need to divide it by 2, right? Because that's to be divided by the standard deviation squared.
Oh, that's the variance?
There, this is the variance here.
Okay.
What's that?
Why is it 2?
Because remember that x minus mu over sigma is the normal, right? This is the variance here. So I have to divide by the square root of the variance. Does that make sense? Okay. All right. So if I'm going to divide by 2 on the inside here, really I'm dividing by what? I divided on the inside to make this look like the standard normal, right? But it's inside the square. So what am I really dividing by? 4. So if I'm going to divide by 4 in here, if I'm going to divide by 4 in here, where else am I going to have to divide by 4?
Everywhere.
On the other 2 pieces, right? So we want the probability that we have 15.364 over 4 less than or equal to that, less than or equal to 20.096 over 4. If I actually do the division here, what do we get? 3.841 and 5.024. I did my arithmetic correctly in my head. We'll find out in a minute because we're going to have to go find these values somewhere. All right? We're going to use the table, yes. So the problem's rigged so you can go find them in the table. So anyway, this is now what we've converted this probability to. Now, why did we go through the pains of changing this to standard normal, right? X minus 7 would have been normal itself, correct? But why did we do standard normal? Why did we divide through by the variance, the standard deviation here? Yeah, good. So the reason why we had to convert it to standard normal is because the theorem says that if we do it the square of a standard normal distribution, it's chi-square of 1, right? So just to write this down, since x is normal on 7,4, we know that z equal to x minus 7 over 2 is normal on 0, 1, or standard normal, which in turn tells us that z squared, or the x minus 7 over 2 squared, is chi-squared of 1. That's why we went through that work. Okay, so again, thinking about how we attack, we're not done with the problem, but just thinking about how we attack the problem, trying to give an example here of illustrating what the theorem is telling us. The reason why we knew to attack the problem this way is first we saw a square of a normal variable, right? I saw the x minus 7 squared. That was what was inside the parentheses. I saw the square of a normal variable which said, hey, I probably want to do chi squared. To get it to chi squared, I needed to divide out by the standard deviation and I get a standard normal. So I already got the mean subtracted, but I need to divide this by the standard deviation to make it standard normal. Then I have chi squared. So that tells me now I can go look at the table. And I scanned the table earlier today so that I could pull it up on the screen instead of trying to hold up the book and say, here, look at the table. Okay. All right. Here's your chi-squared table. We want the chi-square of 1 because it was 1 degree of freedom here. So here is the 1 degree of freedom row. And like I said, I'll know if I did my division correctly if the numbers appear on the table. So the problem's rigged so that you can look them up. Do you see the 3.841 and the 5.024 in the table? Yeah, they're over here, right? Here's the 3.841, here's the 5.024. Right? So notice that, again, these numbers at the top are the probabilities, the cumulative of probabilities associated with those values, or they're the percentiles, right? The 3.841 represents the 95th percentile. The 5.024 represents the 97.5th percentile, right? So, in particular, if I go back over now to the other sheet where I was, I don't remember where I was. Yeah, thanks, Haley. All right. All right. So from the table, we notice that the probability that our x minus 7 over 2 squared is less than or equal to 5.024, that's 0.975, right? And we know that the probability that the x minus 7 over 2 squared is less than or equal to 3.841 is 0.95. Nope, I mean less than or equal to. Because from the table is always set up to look for less than or equal to. All right? This was in the 0.975 column, this was in the 0.95 column. Okay? How am I going to use these two values then to give me the probability that I want? What do I need to do? Yeah, I better subtract them, right? This gives me everything below 5.024. This is everything below 3.841. So if I want what's in between, we're going to subtract 0.975 minus 0.95. And get 0.025. We okay with that? Morgan.
So, can you explain how you knew to subtract the two?
So, what comes out of the table is if I think about the graph of a chi-squared looks like this. Okay? The table gives you the 5.841 would tell you it's that area. And this area is 0.975. Okay? And then if I do the 3.841, we get this area, color it this way. And the table tells us that red area is 0.95. And we want what's in between. We want this part right here. So that's why we subtract. One of the I did this because I really hadn't gone through I hadn't done any problems with normal distribution at all. We'd only done the one problem with chi-squared. I wanted to give you another example of chi-squared reading the table. And the other reason is because this kind of thing we're going to do with subtracting or adding or things is stuff that we're going to do with a normal distribution a lot with solving problems. Questions on that one? All right. Well, let's talk a little bit more about some normal distribution problems then. Maybe. Let's see here. Let's look at this 3.6-7, which is also in the book. So this problem tells you that you've got a normally distributed random variable, mean 6, variance 25, and it asks you to calculate these various probabilities. All right. So to do this, we need to be able to, we could actually do this with a calculator or with Excel pretty quickly. What I want to do is talk about how we do it with a normal distribution table. So this is also a table that's out of your book. It's actually on the page after the chi-squared distribution. So I believe it's page 584. So this is what your normal distribution table looks like. They give you the picture at the top. Just the picture is telling you what area under the curve is being computed by these values that are down on the table. Okay? So basically what it's telling you is this is a table of CDF values. Remember last time we said that for the standard normal distribution we use the phi, the capital phi, right? For the cumulative distribution function. So that's what all of these values are. You can tell that pretty quickly from the first value. This says, the way you read the table is you use, well, we calculate z-scores, but this is setting for your z value that you're plugging in. This would be 0.00, so you're plugging in 0 there, right? Notice that this PDF is symmetric about the y-axis. We talked about that yesterday, or Monday, whatever day it is. Lost track of days. Okay. So this at 0 splits it right in half, right? So if I'm looking to the left side of 0, that's half the area, right? It's symmetric about the y-axis, that's half the area. So we get a 0.5 here for your CDF value. Right? So one of the things that this tells you actually, for a normal distribution, this is standard normal distribution. One of the ways we can see that, of course, is with the PDF. We didn't subtract anything off the variable here, right? Remember the PDF, the general PDF is x minus mu up in the exponent in the squaring, right? Nothing's being subtracted there, so it must have a mean of 0, right? So this mean is 0, but what else, relative to this area then, what else can I say that the 0 is? It's the median, right? It's the 50th percentile. So the mean and the median are both equal. There's also one other thing that you could say. We also talked about mode being the highest possible probability back in discrete ideas. Well, the mode is also defined for continuous distributions to be the maximum. Do you see a maximum here? Where does the maximum occur? At 0. So the mean, the median, and the mode are all the same for a normal distribution. So we can see that, well, from the picture in the table here. Okay? So all three of those values for a normal distribution are equal to each other. So a couple other properties that they use out of this, of course. This last property here is basically telling you how to do complements, right? It's complements and symmetry. Sam, do you have a question?
Yes.
Yeah, okay.
For the normal distribution, where does it turn from concave up to concave down?
Well, you
Does it
could
turn like exactly at 1.5 or?
no, it's something multiple of square root of pi, if I remember correctly. It's some square root of something. You just need to take the derivative of this and set it equal to 0. Set the second derivative equal to 0. Sorry, I'll need to take two derivatives and set it equal to 0. It's a fun calculus problem. You just have to get, it's the square root of something. I don't remember exactly where it is. But it's going to have a square root of pi in it because of this thing's going to be tagging along for the ride. It might be square root of, I don't remember off the top of my head. I'd have to go through the actual derivatives. It's not something that pops up very often. It pops up, it just doesn't pop up very often. It's good problems to ask for homework. All right, anyway, let's look at this particular property here. Because this is one of the things that you have to be able to do, I have to be able to use to get the table to work in all cases. So we know that, let's just think about it from the picture standpoint here. If I have negative z down here, this area would correspond to the CDF of negative z, right? We agree with that? Okay. Well, notice that again, this is symmetric about the y-axis. So if I go up to here to z and color in the corresponding area, this is still phi of negative z up here, right? We agree? That's just using the symmetry of the graph, right? Okay. Now, if I go down here and change my color, if I look at this part, how can I express that red in terms of the CDF? How can I express the red area? That's phi of z, right? We agree? Because I just went from z and went to the left, right? So in terms of the red area, what must this piece be? It has to be 1 minus because all the total area has to be what? It's a PDF, so the total area has to be 1, right? So this part up here has to be 1 minus phi of z. So that's why those two things have to be equal to each other. Does that make sense? Yeah, Michael.
Okay, so we're only considering, like, we're only talking about like one phi of negative z at this point, and then everything else is 1 minus. I'm so confused by this picture.
Okay, so all I'm trying to do by the picture is show you why this equation was true. That's all I was trying to get at from the picture. Okay, so go through it again here. All right, so here's 0, right? If I have a negative z, if I go this way from negative z, this area is phi of negative z, right? So if I flip it to the other side, this is just symmetry. If I go, this area has to be the same as this area. So this area is also phi of negative z, right? Now, again, using the CDF idea, this area has to be phi of z. Because it's going from z down, right?
Yeah.
That's what the CDF means, right? We start at the value and go backward or down, or everything up until that point. We also know that absolutely everything adds up to 1. So I can also calculate this same area is 1 minus this one. And so that's why those two things are equal to each other.
And then we can do the same thing for calculating the orange area as well.
Yeah, you can do the same thing. Yep, absolutely. Yep. All right. One of the reasons why we need this particular property, though, is if we're using the table, notice the table doesn't give us any values for negatives, right? Okay. So the way we read the table is, for example, if you want phi of 1.82, says you were looking for that value. Okay. So the way we read it on the table is, here's the 1.8 row. So you use the whole number part in the first decimal. So there's the 1.8 row. And go over to the 0.02 column to pick out this value right here, that 0.9656. What's that? Because that's the second decimal place. Yeah, so you look for, I'm sorry, I didn't say that explicitly. Thank you for asking though. This is the whole number in the first decimal place along the left column. The second decimal place is along the first row. Okay. So it says I want 1.82, I went 1.8 down for that row, and then across over to 0.02 for the column to get that value.
The reason they had it listed out this way is just because it's too long, just list everything.
Yeah, it'd be, you'd basically need 2 pages of 2 pages of table, essentially. Yeah. Yeah, great stuff.
Why do we use the cumulative one and not?
You can use either. That's just because actually, if you look in your book, the next page is the one that starts in the middle. The reason why I'm doing it with this one is because if you're taking the actuarial exam, that's the one you're given on the exam. The other reason is because then we can express answers in terms of the CDF. I can write down my answers like this with the CDF. So they use the cumulative table. But if you really want to know my 100% reason why I'm using it is because that's the table they give you on the test.
I just like it. I use the other one.
I teach with every other class I teach, I use the other one. This is the only class where I use, well, that's not true. I also teach next semester's class with the same table. But again, the only reason why I use this one instead of the other one is because of the actuarial exam. It's not bad though. I mean, once you get used to it, I think, like Haley said, I think it actually kind of flows a little bit better with the material that we're doing. I know, I just have to learn something new. Sorry.
It's not that new.
It's not that new.
Never. It's not like I've never.
Yeah. All right, so let's see how we can use this table then to answer the questions that I was talking about. I can find it again. So there it was. All right, let's look at this one. All right, so we want to calculate the probabilities that x is between these values or outside of values or absolute values of it, whatever, it doesn't matter. So the table that we have is for standard normal. The x is not standard normal. So what do you think the first thing we're going to do is with all of these problems? Convert it to standard normal. So to convert it to standard normal, what am I going to need to do to the x in this case?
You're going to need to subtract 6 and divide by 5.
Good. I need to subtract 6 and divide by 5. Exactly. Yep. So for A, if I want to do the probability that 6 is less than or equal to x is less than or equal to 12, this is the same thing as the probability that, well, you just told me I need to subtract 6 and divide by 5, right? If I do it in the middle, where else better I do it? Everywhere else, right? 6 minus 6 over 5, 0. Okay? 12 minus 6 over 5, 6/5, which is 1.2. The only reason why I converted it to a decimal is because I have to look up a decimal in the table. Okay? Is this okay so far? Yeah, Megan.
For the last problem, we didn't subtract by 7, did we?
It was already given to us in the problem as an x minus 7. So the mean had already been subtracted for us.
Okay.
That was why we didn't do it. Okay. In general, especially with normal distribution problems, they won't have subtracted the mean for you, so you'll have to do it. Okay. Just in that particular problem, they gave you this x minus the mean.
So even though it's normally distributed, I guess you can't say always, but a lot of times convert it to a standard because that's
the table. That's how the table is, yeah. So that one's pretty much as close to always as you can get. You'll always go over, you'll always convert it to a standard normal so that you can use the table.
Okay. Are we going to be given a table?
Oh yeah, I'll give you the table. You don't want to memorize it?
No, I mean like in a
Yes.
sheet?
Yes, I do.
Or do we have to go look it up in the book every time we do it?
I'm pretty sure you'll give us a sheet.
I'll give you a sheet for the test. You mean for your homework? What's
Well,
wrong?
the homework's in the book anyway.
Yeah, if you would like me to make copies for you so that you can have a separate sheet, I will give you that to you. Would you like me to do that?
No, don't kill me.
Will you think that I'm picky if I say yes?
No.
Yes.
All you have to do is just ask.
I will think you're picky.
Well, we don't care what Michael thinks about you.
What?
She does care because
Grace, your responsibility though is to remind me before Friday to make copies so that I can distribute it.
Okay.
Okay.
Does everybody else want to copy? No.
Yes.
I
Yeah.
don't want to kill trees.
See, I'm not the only one.
I don't want to kill trees.
Oh, too bad. I'm going to kill a tree for you anyway. I'm going to kill a tree in your name. I'm going to go chop the tree down, and I'm going to put a little plaque next to it and said, Michael killed this tree.
No.
I just sent them the axe. You need to yell Michael.
That's rude. That's
All
rude
right.
to the tree.
All right. So let's talk about how we can convert this over so that we can use the table. If this less than or equal to sign weren't here, and we just had this, how can I express this in terms of the CDF?
Like that.
Phi of 1.2, right? This is now standard normal, correct? So it's the standard normal variable less than or equal to 1.2. That's phi of 1.2, correct?
Yes.
So this would be equal to phi of 1.2.
I don't.
Now phi of 1.2 goes everywhere below 1.2, right? Where do I want it to stop? 0. So what do you think I should do to this so that I know that I want to stop it at 0? What do you think I should do? They better subtract the phi of 0, right? Going in between those two intervals, right? Just like the picture we did before with the chi-squared. Remember I told you one of the reasons why I wanted to go through that chi-squared example was to do the subtraction, right? It's the same concept here, right? Subtract it off. Well, phi of 0 is always 0.5. We know that splits it in half, correct? The other one, we want to go look up at the table.
Go ahead and guess.
I'm not gonna look at it.
I didn't know.
I'm gonna say like 0.6.
I'm still more like 8 now.
Oh, you're right.
Where is it? Where is it?
On the left.
Well, what number do we need to look up in the table if we want phi of 1.2? 1.2
It's right there.
and
That
0.
is damn close.
You were.
Not everybody.
This is really proud of herself.
She should be proud of herself. That was pretty good. All right, so 1.20.
I've seen this table before. You have better judgment.
All right, so 0.8849.
100% sure.
Yeah.
I agree.
All right, so back over here again. This is 0.884. Did everybody see where I got that number from?
Yeah.
Okay. All right, so we'll get 0.3849 for a final answer.
Dr. Joe, I did that math for you.
Thank you.
Proud of yourself.
Okay,
All right, let's do the next one.
let's do the next one.
I don't have enough space for these.
Ability.
All right, so the next one is probably between 0 and 8.
0,
Yep.
It's 2. Negative 2. That's C.
That must have been C.
Whoa, X is negative. It's between -6 or 5.
All right, so again, our first step is to do what here? Subtract 6 and divide by 5. Why are we doing that again?
Because it needs to be unit normal. Is that a thing?
Standard normal.
That's what I'm calling it from now on.
Unit normal?
Unit normal, guys.
Okay.
What's it usually called?
Standard normal.
Well, I like unit normal. So. What's gonna be?
One on the left is negative 1.2.
Okay.
And the one on the right is
Oh my god.
and that's like
Everybody okay with those values? Haley's not okay with those values. It's okay.
This is just gonna be one.
All right, so in terms of the CDF, how would we write this? Okay, cool. So well, this is good so far, right? Phi of the right endpoint minus phi of the left endpoint.
Oh, Dr. Joe, then we distribute, right?
You what? This okay for this part? Now, can we look up 0.4 in the table? Yes. Can we look up negative 1.2 in the table?
No.
No. What can we look up in the table? 1.2, right? So how do I convert that second one into something that we can look up in the table?
1.2, b of 1.2 minus
1 minus 3. Oh. That's all just.
We did it.
Right? Everybody see where that part came from? Right? This, sorry, go ahead.
Is that from like the picture?
That was from the picture that I drew, yeah.
This is my favorite one.
So basically what we're doing is, the idea here is that when we do this negative, we flip back, we're flipping back from the left side to the right, it's changing less than or equal to greater than or equal to from the symmetry, right? It's a mirror image, right? It's changing the less than or equal to a greater than or equal to. That's why we're doing 1 minus this, so we're calculating the complement. So they're going from here to here is using the symmetry, but the symmetry is mirror image. It's mirror symmetry, right? So less than or equal to becomes greater than or equal to, so I got to flip it around again with the complement. That's why I have the 1 minus in there. Yes.
So in terms of the picture, that would be like negative 1.2
Yeah.
over
Mm-hmm.
and then 1.
Yeah, that's right. That's exactly right. Yeah, thank you.
So when we're because like I noticed in the last problem too, you put like the second number first. Is that always the case? Like 0.4 goes first, and then the negative 0.12 goes second.
Yeah, it's like what you do with the fundamental theorem of calculus. You're doing upper endpoint minus lower endpoint. It's the same kind of idea. It's actually, it literally is the fundamental theorem of calculus. We just don't have the antiderivative, right? So capital C is just the name that we're giving for the antiderivative. We just don't have it. So that's why we're using the upper minus the lower. Okay. All right, so then we need to look up these values in the table. Back over to the table here. We already looked up 1.2 in the table in the previous one, right? 0.4 would be right here, right? And you get 0.6554. Okay, so go back over again. So this was 0.6554, and then we had 1 minus 0.8849, was that one? I remember right? So what do we, this is 0.1151, so we get 0.5403. We'll pretend like I did my arithmetic right.
Good job, Joe.
Thank you.
Yes, you did it right.
Oh, good. I may have done arithmetic once or twice in my life.
Really?
Really, I wouldn't believe it.
What's the probability?
Arithmetic, probably one. Guessing. All right, is this one okay with everybody?
You did
Yep.
probably just.
All right, let's do one more here. Make sure we're all on the same page. Let's look at part D. Notice you're going to do part C the exact same way. The quote-unquote tricky part with part C, what's the difference between parts A and B and part C? What's the only difference, besides the numbers, what's the only difference that you see?
It's not equal to.
Yeah, there's a not equal to here. Does that matter? No, because why? What kind of distribution? What general kind of distribution is a normal?
So at 1 point, the probability is 0.
Good, exactly. Yeah, it's a continuous distribution, right? And for continuous distributions, the probability that you're actually equal to the value is 0. So, good. So this one's you're going to attack C just like you attack D. Let's just, like you did A and B. Let's just look at D just to give a different one here. So for D, you've got the probability that X is greater than 21. Again, first step is to do what?
Can I use the unit?
Yeah, use the unit normal, according to Grace. Standard normal.
It would make sense.
True. So 21 minus 6 is 15 over 5 gives me 3.
Three?
3?
3 is a pretty big number
For a normal distribution, 3 is a pretty big number.
relative to other numbers.
Relative to other numbers as well. Sure.
It's pretty big.
Well, it's a million times bigger than 3 millionths. So
Yeah.
Very insightful.
thank you. All right. How can I express this in terms of the CDF?
1 minus less than, or less than or equal.
Okay. So I can do, if I think about flipping it first, I can certainly write that as 1 minus the probability that it's less than or equal to 3. Right? And so now this would be 1 minus what? Phi of 3.
See the table.
See the table?
Give it to you.
So phi of 3 is
Way.
0.9987 down there.
Which means this probability equals 3. Something like that.
You want to see if I can do it?
This is his moment.
I did it when I read the value.
Yeah.
Yeah, Megan.
So we're just switching it because it has to be less than or equal to 3?
Correct, because in the table it all has to be less than or equal to probabilities. That's why we flipped it. Yep. That's exactly right. Is okay? The idea makes sense?
Pocket like this.
All right, so let's see if we can do another one here. Let's see if I can pick one out. Let's look at 23.3 here. This should be in the packet of problems that I gave you. What I should do is make my TA set up the individual pages and then she can label them.
Yeah, you should do that. Make her do more work.
Yeah.
So when you do the word problems, is it in the exclusively submitted?
She gets paid.
She doesn't need to say that it's a normal distribution. Yeah. All right, so we've got a normal distribution, mean 1, variance 4, and then it wants us to figure out this particular probability.
You got it.
All right, so notice that we have a quadratic here. I said a lot of times you think about when you do the square of a normal, you think chi-squared. I don't want to attack it this way in this case. Okay. Not that you can't, you just have to complete the square to do it, and I don't feel like doing that. I have to have a perfect square here, I don't have that, so I don't want to do that. All right, so let's do this instead by how you would solve inequalities back in algebra class. I've got a quadratic inequality. What would I want to do first before I do anything else?
Factor out.
Nope, that's not it.
Pull it all in.
What do I want to do first? What was it?
Pull it all in.
Put it all on one side. Good. Because factoring out an x doesn't help us here because why? Why doesn't that help? Well, the 8 didn't have an x for one, but also that if I have two numbers that multiply together to give us 8, does that tell me anything about either of the two numbers?
No. You?
Except for the fact that they're not 0. It's the only thing it tells us, right? Okay. There's lots and lots and lots and lots and lots and lots of different numbers that multiply together to give you 8. Right? Now, it didn't say integers. It said lots and lots and lots of numbers that multiply together to give you 8. Right? Okay? So the first thing I need to do is make this a 0 on one side. Because when I do a product that's equal to 0, I do know something about one of the numbers. Right? Okay? Can we factor this?
Yeah.
Yeah. What does this factor as? Okay. All right, so I need that product of x minus 4 and x plus 2 being less than or equal to 0. All right, Well, first, what does it equal 0?
4 and negative.
And 4 and negative 2, right? That gives it's equal to 0. But we can also have negative here, right? 4 and negative 2 are important endpoints. But what else can make this inequality true? Not just 4 and not just negative 2. What else can make it true?
If it was less.
Well,
Anything greater, no.
Anything that makes
Anything
X
between 0 and 4.
We gotta do that number line.
Okay. If you don't see it right away, how about a number line thing will kind of work.
There you go.
The idea behind the number line thing is you're thinking about just what the graph of the function would look like, right?
Yeah.
Put in something less than negative 2.
Negative.
Negative 3, okay. Negative 3 in here is negative. Negative 3 here makes negative. Negative times negative makes positive, right?
Good job, everybody.
Right?
Yeah.
What'd you say?
I said, good job, everybody.
Good job, everybody. Pick a number between negative 2 and 4.
3 halves.
Okay, it doesn't matter. Okay, 3 halves. Sure. This one's going to be
Wait, excuse me?
negative. This one will be positive. So the whole product will be negative. And then negative will be positive. Another way you could have easily seen this, hopefully. If you think about the graph of this, what's the graph of this going to be?
Parabola.
A parabola? Okay, sure. Why not? A mispronounced parabola.
No.
Sure.
Parabola.
A parabola's? Okay. If it's a parabola, which way does it go? Up or down? Up, because it's positive here, right? So it's going to have to come down, hit the x-axis, go back up again, right? So between negative 2 and 4 is what it might be below the x-axis, right? Which is exactly what we want, is below the x-axis, isn't it?
Interesting.
All right. So how can I convert this probability statement then? What does x have to be in between? Negative 2 and 4. Now it's set up just like the other problems, isn't it?
No.
I thought your energy level was lower today, Michael.
You make it really funny when you just shit around.
Please don't do that in the classroom. All right. What do we do next?
X minus 1 over 2.
Good. Sounded very robotic.
I was saying
X minus 1 over. Okay, x minus 1 over 2.
And then negative 0.75. Wait, did I math wrong?
3 halves, right?
Oh, yeah.
Yeah, and then 3 halves?
Yeah.
Okay. And then if we want to express this in terms of the CDF,
Let's do B of 1.5 minus 1 minus B of 1.5.
okay. So I'm going to write, I'll just do the step of just writing it as minus, phi of minus 1.5. And then Michael did the 2 robotic steps at once. Right? You can change the phi of negative 1.5 to 1 minus phi of 1.5. And if I just do a little bit of algebra, I can do it as 2 times phi of 1.5 minus 1.
Whoa.
Yep.
And then we leave that as our final.
Or go look it up in the table.
Whoa, that's wild.
What, looking it up in the table?
No, you like.
Oh, I did algebra?
Yeah,
Oh.
You algebra it, and I just was surprised by the algebra.
0.99332, we agree, for 1.5?
Yeah.
Right here?
What is it?
0.9332.
It's gonna be quicker.
866.
So they probably Grace because I didn't care. But what did I say it was again? 0.9332?
I guess so. I don't know.
And so you got 0.8664?
Let's see.
That's so it is kind of fun to race back here. You're pretty fast.
You're using a calculator too.
I can't do that in my head.
Sure you
That's why I can't.
You
It's just-
could.
It would take me significantly longer than it would.
That one's easier to do in your head because all you have to do is double it and just drop the 1.
8, 6, 6,
4, yeah. That one's not
Oh,
hard to
yeah.
do.
You
Yeah.
drop
You just
the
drop the 1. That
Well,
one's easy. All right. So that's the kind of problems that you come up against with normal distribution. We'll do a couple more next time, and then we'll probably get into chapter 4 where we'll start doing some bivariate distributions, joint distributions. We're going to have 2 variables instead of 1.
Darn it, Dr. Joe. I just